What up, what up, what up? 5.6, y'all. Arithmetic sequences. All right, so it might seem like we're taking a little detour from functions because I'm talking about this thing, arithmetic sequences, that you might not know about, but we're not. Arithmetic sequences, if you keep functions and linear functions in your mind while we're talking about this, you'll notice that there's a lot of similarities because an arithmetic sequence can be defined by a linear function. So let's kind of clear up this idea of what a sequence is, because I'm not going to keep saying it and have you not understand what I'm talking about. A sequence is an ordered list of numbers. Okay? Very simply put, ordered list of numbers. If I can manage to write on here. That's much better. Now, each number in a sequence is what we call a term. Just a little bit of vocabulary for you before we start off. Each a sub n has a specific position n in the sequence. Okay, so this is where a little bit of notation becomes weird. We consider each term in the sequence to be an a, right? And then the little subscript number here tells me which term it is. Is it the first term? Is it the third term? Or is it up to the nth term? Nth term meaning it could be any number. It just goes on and on and on forever. Okay, so this, when I say a sub n, that means that I'm talking about like the whole sequence, or like a number in there that I don't know yet. It's an unknown, just kind of like an x. But when I say a sub 1, I'm talking about the first term. When I say a sub 3, I'm talking about the third term. A sub 27, I'm talking about the 27th term. So in an arithmetic sequence, the difference between the consecutive terms is the same. Right? I said there's a lot of similarities between linear functions. That's the same thing that we were just talking about with how to define something as linear or nonlinear. They had to have the same difference, the same constant rate of change. So this difference is what we call the common difference. All right? And each term is going to be found by adding the common difference to the previous term. So let's talk about how we can take a sequence and just build off of it. All right, I have a sequence that starts -7, -14, -21, -28. So what is it that's happening each time? Each time it looks like I am basically adding -7, or just subtracting 7. Right? This is -7. From here to here is -7. From here to here is -7. So if I wanted to write the next 3 terms in the sequence, I would have to take this one and subtract 7. Take whatever I get here and subtract 7. And so on and so on and so on and so on. So my next 3 terms should look like 28 minus 7, which is -35. -35 minus 7, which is -42. And -42 minus 7, which is -49. So those would be the next 3 terms that would come in my sequence. Easy enough, right? Finding the common difference and then applying it to find the next few terms. Now let's look at what happens when I try and graph one. Okay, so what am I going to be graphing basically? Because all I see here is a sequence 4, 8, 12, 16. What am I supposed to graph? Because when I graph, I usually have an x and a y. So what I'm going to graph is what term it is versus the value of the term. So like I said before, this is going to be a sub 1, the first term. This will be a sub 2, the second term. This is a sub 3, the third term. And this is a sub 4, the fourth term. So let's graph that. It'll be a sub 1, a sub 2, a sub 3, a sub 4. Versus which value it is. So let's do 4, and 8, 12, and 16. And let's see what it looks like when I graph them out. A sub 1 is 4, a sub 2 is 8, A sub 3 is 12, and a sub 4 is 16. What? Cool it, y'all. I think I just graphed a linear equation. And that's another one of those things that I was saying. These arithmetic sequences relate so closely to linear functions because they represent linear functions. Okay, that's a very, very important piece to remember. Alrighty, so now let's take a look at what we're doing here. You can use the first term and the common difference to write a linear function that describes the arithmetic sequence. So let's go ahead and try and figure out what function or how I can define this arithmetic sequence. Okay, so I'm going to talk about the position, the n position, right? We talked about on this last page, right over here, a sub 1, a sub 2, a sub 3, a sub 4. Those little subscripts, the 1, 2, 3, and 4, those are defining the position, which term it is. Okay, so position 1, 2, 3, 4, all the way to the nth position. And then what that term is, the first term, which we were just talking about before, would be the a sub 1 term, the a sub 2 term, the a sub 3 term, the a sub 4 term, all the way to some a sub n term that we don't know yet. Now, how can I write these numbers in terms of adding that common difference? What was the common difference in the last one? We went 4, 8, 12, 16. So it looks like the common difference was just some value like 4. I think 4 plus 4 would be 8 plus 4 would be 12. Yeah, so the common difference would be 4. So how can I write all of these terms just with a sub 1 and a d? Well, a sub 1 is easy because that's just a sub 1, right? But how can I write a sub 2 using only a sub 1 and d? Well, a sub 2, let's see, this was 4, this was 8, and this was 12, and this was 16. A sub 2 was really the first term plus 4. So that's a sub 1 plus d, the common difference, which was 4, right? 4 plus 4 was 8. Now, if I go on to the a sub third term, I'm stuck again because I can't say a sub 1 plus d because that's only 8. It doesn't get me to 12. But I could add 2 d's, right? A sub 1 was 4, and if I add on 8, 2d, I could get 12. Now the next term, a sub 1, I wonder if I can keep this pattern going and add 3 d's. 3 d's is 12. 4 plus 12 is 16. Perfect. So now let's see if I can create a general rule. A sub 1 plus how many d's have I added every single time? Well, in the second term I added 1d. For the third term I added 2 d's. For the fourth term I added 3 d's. So it looks like I always added 1 less than the term. So what I'm going to add here is 1 less than the term times d. Now that might seem a little bit strange, but we need to try and wrap our heads around this idea, because what we just made here is a formula for an arithmetic sequence. And it's really, really cool that we were able to just kind of work our way down. And if you can wrap your head around where these d's came from and how I am taking 1 less than the term each time. I had the third term, I took 2 d's. I had the fourth term, I took 3 d's. Then this formula is going to make a lot more sense to you. All right, and in terms of numbers, I was kind of saying this as we went along. A sub 1 was 4, a sub 2 was 4, and then plus the common difference, the d was 4. And then the next one, a sub 1 was 4 plus 2 d's, 2 times 4. That got me my 12. And then here, 4 plus 3 d's, which again, 4. That got me my 16. And then here, if I wanted the nth term, I could do 4 plus whatever n term it was, minus 1, times the 4d. Alrighty. Formula alert, formula alert. Equation for an arithmetic sequence. We just did it. Any particular term that you want, a sub n, can be defined by the first term a sub 1 plus n minus 1 times the common difference, where a sub n, right, we've talked about this, is just some term way out there. It's some distant term that you are looking for. Okay, so term, where'd my R go? You are looking for. The a sub 1 is your first term. The n is going to be the position. And d is the common difference. Now let's look at how we can use this. Write an equation for the nth term of each arithmetic sequence. 4, 11, 8, 5, and then find the 50th term. Now finding the 50th term would be absolutely ridiculous if I had to write out 50 terms. But I can easily do that if I can write an equation. Okay, so my equation is going to look like this. Any particular term that I want to find, a sub n, is going to equal the first term of the sequence, right? A sub 1, which is 14, plus n minus 1 times the common difference. Now that's the tricky part. What's the common difference here? 14 to 11 looks like subtract 3. 11 to 8 looks like subtract 3. 8 to 5 looks like subtract 3. Awesome. So my common difference here looks like it's adding a negative 3. So my common difference is minus 3. Now if I want to make this look a little bit nicer, I can distribute and combine like terms. So this is going to be 14 plus negative 3n, and then plus 3. So when I combine like terms, a sub n equals negative 3n plus 17. Nice. Now the trickier part. I have to find the 50th term given this information. So that means that I'm not looking for a sub n anymore. I'm going to change to a different color. I'm looking for a sub 50. So the n in the equation is now a 50. So that's going to equal negative 3 times 50 plus 17. Plus 17 seems pretty small now. So negative 3 times 50 is going to be negative 150 plus 17, which equals negative 133. So the 50th term, a sub 50, is 133. Now that would have been crazy to try and do without making a formula. It would have taken forever. Now let's look at our last example. Online bidding for a purse. Ugh, purses, am I right? Huh. Increases $5 for each bid after the $60 initial bid. We want to write an equation for the nth term of the arithmetic sequence. Okay, so that should be easy enough. We're getting pretty good at this. So let's try it out. A sub n equals the first term. So we're going to put that 60, that first term, right in here, a sub 1. And then plus n minus 1 times the common difference. Now what's the common difference? 60 to 65 looks like plus 5. 65 to 70 looks like plus 5. So it looks like my common difference is 5. Distribute and make it look pretty now is the name of the game. So 60 plus, and 5 distributed in here is 5n minus 5. And then my rewriting step comes in. A sub n equals 5n. And 60 and negative 5 makes plus 55. Beautiful. So now what term do I need to find? The winning bid is $90. How many bids were there? Ooh. So it looks like we're changing things up a little bit. I've been given that the winning bid was $90. Right? How many bids were there? I'm given what the a sub n term equals, which is different. And that's going to be a kind of a tricky thing to recognize. I'm not going to try and look and try to find the 90th term here. I'm trying to figure out what term produced a $90 bid. So what this tells me is that a sub n equals $90. Now I want to figure out what that n is. I want to say the 12th term produced $90. So if I know that a sub n equals this formula, but a sub n also is $90, I can set them equal to each other. 90 equals 5n plus 55. And then all I should have to do is solve. I'm going to subtract 55 minus 55. And I'm going to bring this up here so I have more room. That's going to be 35 equals 5n. And then, just to get n by itself, divide by 5. And I'm almost there. I can feel it. N equals 7. Beautiful. So what does this mean? This means that I had 7 bids. And on the 7th bid, a sub 7, it was $90. And the bidding was over, and you won. You got the purse. Congratulations. $90 for a purse. Good stuff. I think that is it for today. That's it, arithmetic sequences. Just remember how closely they relate to linear functions. That's one of the big things about today. Make sure you try out those problems, do your absolute best with them, write down any questions you have, and we'll talk about it in class. Fare thee well, everyone.